Welcome to 11.3, the tangent line problem. This is going to be your final notes for pre-calculus trigonometry, and congratulations. Hopefully you've made it through the class successfully. So the tangent line problem, here's where we finally tell you what the difference quotient means if you put the limit as h approaches 0 in front of it. What it allows you to do is it allows you to come up with a formula, whether it have an x in it, an x squared in it, x cubed in it, no x's at all. It gives you a formula so that you can find the slope of a tangent line to any curve at a specific location. So previously, when you were in Algebra 1, hopefully, your teacher was very strict with you about graphing parabolas. We never use a ruler, ever, when we're graphing a parabola, because it is constantly growing or shrinking, depending on which way you're graphing it. And a line shows that there is a constant growth. Well, it's not constant at all, which is why there's an x squared on a equation for a parabola. What the tangent line problem allows us to do now is it allows us to find the slope of the tangent line. Remember, tangent line is a line that kisses a graph just at one location. It doesn't actually go through. It's just got a single point of intersection. What this allows us to do now is actually find the slope of a tangent line at any point on a curved graph. You don't necessarily now talk about slope only for lines. So we can now find the slope on a parabola when the x value is 19, or on a cubic when the x value is negative 23. That's what this allows us to do. So now we're just going to practice it. So we're going to use the definition of the derivative. Well, the definition of the derivative is the limit as h approaches 0 of the difference quotient of that f of x function. So the definition of the derivative, we got to take that out. So this is the limit as h approaches 0 of our f of x plus h minus f of x all over h. So we practiced difference quotient first semester for a reason. This was why. And remember that this is the first derivative. Finding the first derivative, so I'm just going to go ahead and set this equal to, it's f prime of x. So f prime of x is equal to the limit as h approaches 0 of the difference quotient. I'm just going to go ahead and keep that f prime notation on the left-hand side, and I'm just going to work down and start plugging stuff in. So this is just like the last unit. I'm just going to go ahead and plug in the difference quotient and do some algebra. So I've got it plugged in. I'm going to go ahead and distribute and then combine like terms and see what happens. At this point, it's still the difference quotient from first semester with a limit attached to it. So everything without the h's had better cancel. If it doesn't, we made a mistake. So I still haven't evaluated my limit, which means I'm carrying it with me the entire time. So the limit as h approaches 0. Now looks like I have negative 7h over h. My h's cancel. So I have the limit as h approaches 0 of negative 7. There's no h left anymore, so this is just negative 7. If there was an h to plug in, you'd plug it in. So what this is saying is that f prime of x is equal to negative 7. Remember, f prime means we're talking about the slope of the tangent line formula. So this gives us a formula. Well, there's no x here, so I don't even think of a formula. I see a constant. What this means is that the slope of the tangent line is always negative 7. Interesting. Take a look back at the original function. I gave you the equation of a line. Y is equal to negative 7x plus 1. Hopefully back from Algebra 1, you recognize that the slope of this line is negative 7. If I were to take a tangent line to a line, they sit on top of each other and they share the exact same slope the entire time. So we'd have major issues if we didn't get what the slope of the line was in the first place. When it becomes interesting is when you start talking about something that isn't a line. So here we have a parabola. I'm going to do the exact same thing. Plug in the limit as h approaches 0 of the difference quotient. We'll call that f prime of x. And let's do some algebra. Okay, so I went ahead and plugged this into the difference quotient for the limit as h approaches 0 of the difference quotient, and then I just went ahead and multiplied it all out as well. So again, at this point, if this has been successful, everything without an h better cancel. So my 3x squareds go away, that's good. My 5x's do as well, as do my 1's, good. So now I just have the stuff that's left over with the h's. So I'm going to go ahead and factor that h out while I'm here. Cancel out those h's. I'm not plugging in the 0 yet, so keep that notation with me. Now I'm going to go ahead and plug in the 0. When I plug in the 0, the h term disappears. And now what I have is I do have a nice formula to be able to find the slope at any point on this original parabola. So I'm going to use the 6x plus 5 as a formula. So let's say that somebody wants me to find the slope of the tangent line on this parabola when x is 19. I take out this formula at the very bottom and I plug in 19 for the x value. That's all I do. So once I have the formula, I can now find the slope at any point, anywhere on the entire graph. Okay, well, it looks like they actually, or I want you to use this from the previous one. So over here on this side, I'm going to go ahead and write down what our f prime was. And I think I got 6x plus 5. So now, I go over to my problem. Using f prime from the previous question, I want to find the slope of the tangent line at that specific point. Now, my formula only requires x's, so all I care about is the x. I don't really care about the y at all. The y is there to show you that it was actually a location on the parabola itself. So all I need to do is take out my f prime of x formula, 6x plus 5, plug the x value in, so it's going to be f prime of negative 9. If I plug that in, it's going to be 6 times negative 9 plus 5, which is going to be negative 54, plus 5, which is negative 49. So the slope of the tangent line to my original function is at x equals negative 5 is negative 49. It's a pretty steep line actually pointing down. So pretty interesting. But now you can actually find the slope at that point. All right, let's go over to this one. Notice on number 4 here, all I did was give you x equals 4. This is because I don't need the y. The previous part gave you y, it's extra information. This one, no y, it's okay, you don't need it. So just take out the formula. Note that this all kind of hinges on whether or not you did the previous problem correctly. So make sure that you take your time on that one and watch your notation. So we've got f prime of 4. Plug in my 4. That gives me 24 plus 5, which is 29. So the slope of the tangent line to the original function f of x, when x is equal to 4, is 29. Again, pretty steep, but now it's positive slopes pointing up to the right. So we've basically come full circle. Started at the beginning of the first semester with difference quotient. Didn't really tell you what it meant, told you we'd get to it. And now we've built up to that. Difference quotient, as long as you do the limit as h approaches 0 of the difference quotient, you're actually coming up with a formula to be able to find the slope of the tangent line at any point on the entire curve. I hope that these videos and the notes online have been helpful to you throughout this year, and if you have any questions, make sure that you ask in class.